I'm going to talk about the Oh My Seriously lab. But first, before I kind of explain like circuits and like series and like resistors in series, which just means back to back to back kind of, we got to talk about a fundamental energy principle that's going to kind of be around with you everywhere in your physics journey: the conservation of energy. Why is that important here? Well, what we know so far about like these kind of simple circuits, right? Well, I guess with all like circuits is that there's charge. Battery provides a potential difference, which allows the charge in the circuit to flow, and then this flow, this current, will go through a resistor, and that resistor is going to use up some of the potential of the charge provided by the battery and make light or heat or whatever. So hopefully that makes sense. We need to talk about, well, in this kind of basic circuit like this, right? Resistor 1. I don't know its resistance, but, and we'll figure it out. If you did the lab, you know, like, this is 5 ohms, 10 ohms, whatever. But just to kind of explain this idea, this battery, right, it's going to provide 9 volts of potential. This resistor better use up 9 volts of that potential, right? If it's only using up 6 volts, well, after one loop, it's going to have, the charge is going to have positive 3 volts of potential, right? Because it started with 9, this used up 6, and now it has 3. It goes through the battery, it's going to get another 3 plus 9, another 12, like another 9, right? So it's going to get 12 volts. Minus 6, you have 6 volts total, right? Go through the 9 volt battery, you get 15 volts, minus 6, you're just getting more and more potential energy. That violates our conservation of energy, that energy has to be conserved, right? So the 9 volts given by the battery, this resistor better use up all of those 9 volts, right? So positive 9 volts, minus 9 volts. That's how much energy it's using. So why is this important? And I forgot to add what we're doing to our total, and you'll see how this kind of connects back. But in any kind of circuit, it doesn't matter if there's 1 or 2 resistors, the total of these resistors better add up, or like better remove those 9 volts, right? Or use up the 9 volts given by the battery, right? The resistor 1 here, it's taking up 9 volts. Over here, it's not going to take up 9 volts anymore, because if it takes up 9 volts, there's 0 potential here. There's no energy for this resistor to use up. Resistance doesn't determine, well, I shouldn't say that. Resistance, like just because this is like 10 ohms doesn't mean it's going to always take 9 volts. You can see that this might take up, I don't know, a certain amount of voltage, maybe 3. The rest has to be taken up by resistance 2. The total 9 volts has to be used up. This is called the loop rule, where all of them get added up to 0, right? So the positive voltages subtracted by the used up negative voltage, everything should add to 0. So now that we've talked about that, we can kind of, this lab will make more sense. So in class, if you were doing this, you had like the 9 volt battery and a resistor 1, right? That was the first thing. So we used a multimeter, to get the current and the voltage. So like, for example, to get the voltage, you know, we connected up like the voltmeter or the multimeter. To get the current, we had the ammeter in series, right? So this will measure the current. So the voltage through R1, my data, I didn't get, you know, exactly 9. So for this one I used 6 volts. I'll just change it to 6. Yours should have been 9, so it might be a little bit different. I just said voltage was 6 volts, right? It was like 5.97 or something. Scientists really shouldn't be rounding like that, but whatever. 6 volts, which makes sense, right? It's using up all 6 volts from the battery. So the current was like 0.59. So if you go to your calculator to find resistance, remember, I'll just write it here, V equals IR, right? Just note that. If I want to find the resistance, take the voltage divided by current, you get around 10.17 ohms. Right? So, and I'm not going to, you know, the R total, like, that's the same, right, for both. Right? Everything's the same there. So this resistor was actually, like, it's rated 10 ohms, so this pretty good number, pretty close. So now let's see what happens when we add up two resistors. So first things first, you can get the total current by kind of putting an ammeter right here, right, to measure the current. So this ammeter would read, in this case I got it read 0.25, like 0.25, why am I like blanking? 0.25 amps, right? So that was the total current flowing through the circuit. And if you wanted to measure the total voltage, I got like, once again, you can do this. I got like 8.9, we'll say 9, right? So 9 volts. Hey, this makes sense, right? For the total like for all the resistors in the circuit, like the total resistance, it's using up all the voltage provided by the battery. And it makes sense if you kind of got like a number a little bit lower, right? Because our voltmeter is not perfect. Some of the current will go through here. Less energy will be used up by these two resistors. You'll get something a little bit less than 9 because our voltmeter was using up the rest. So not to like show it's like the voltmeter has battery, so it doesn't need the energy to power it. Otherwise, it would definitely be less than 9 or 8.9. But just because of the wire like heating up. So our total would then, you can do the math, you get 36 ohms. Okay, so I should make this R2. So let's do, if you did the voltmeter, right, if you took the ends and did it for R1, you should have gotten, I got a read of 2.554. For resistor 2, right, if you now just change the voltmeter to measure these two, I got 6.37. This is pretty interesting. This essentially adds up to 9, right? Or it adds up to 8.9 or something, right? So this makes sense. Each resistor is using up a certain amount of voltage. So if this takes up 2.554, the rest, right, 9 minus this, right, the rest of the voltage is used up by resistor 2. So this makes sense. All right, if you measure the current, like by moving the ammeters here and here, what you'll actually get is they each have the same current. And we'll talk about why this is, but 2.58 amps for both. You can use that to calculate the resistances. So if you take this divided by that, I got 10.26 ohms, 216 ohms. So a little bit off, but not a big deal. And then 25.48 ohms. And this resistor 2 is rated at 25 ohms, so that's pretty close. Do you notice anything about these two numbers and these two numbers? They add up, right? If you add these two up, you get around like 35.6 or something, 35.7, very close to 36 ohms. So that's interesting. We'll talk about that. But for right now, let's go on to the last one. We have all three of these. So I'm not going to like go through what I got. I can write down my data though. So R1, I had 0.2, sorry, this is back wrong. I had 0.1 current. And I just, you shouldn't do this in real science. It's bad practice to just take one trial and assume it works forever. But, you should really be putting ammeters at each side to have good evidence. But I'm fairly confident that it would have 1.8 amps for both, if not a little bit off, for the total current and for all three resistors. So the voltage, well, I know the resistance total is going to have roughly 9 volts. You can use data to show that. So the first resistor took up 1.98. Second resistor took up 2.74 volts. The last resistor took up 5.11. All right. And then the resistance, you just divide. So I got 10. So this is pretty easy to divide. So you're actually dividing by 0.1. So you're just like moving the decimal over. 10.98 ohms for the first one, which roughly pretty good. 27.4 ohms, right? And then 51.1 ohms for the third one. And the third one was rated at 47 ohms. So this is getting a little bit off. That's not the end of the world though. Our total is going to be 9 divided by that much, so 90 volts. And these will add up to 90, right? So this is pretty interesting stuff. Like the patterns we're seeing. same current regardless, right? Going through the circuit. So let's do the analysis. Let me just check how much time I'm at. 10 minutes, that's not bad. Excuse me, I just choked. I'll just do the analysis in one video. So the analysis, the current anywhere in a given series circuit, right? When the resistors are all kind of lined up back to back, what is the current? Well, it is constant, right? The current throughout this whole thing is flowing at the same rate. Why? Because you could probably use conservation of charge to also prove it. But the way I like to think about it is that like the resistor is not using up any current, right? Well, that's one common misconception I used to have, is that a resistor, well, I didn't know what a resistor was back then, but like something like a light bulb would use up some of the current, right? But that's not true. It doesn't use up current. It uses up the voltage, right? It uses up the potential. So the current is still flowing through the same, right? Like, and you can get into the physics of like drift velocity and, you know, how like the electrons all collide with each other, because remember, electrons are the ones flowing. You can get into that. University physics is a great textbook that talks about that. But case in point, current is constant throughout a circuit. As you add resistors in a series circuit, the current flowing will decrease. This is question number 7, or second question. And yeah, right, if you add more and more circuits, our current went from 0.6 to 0.25 to 0.1, because there's more resistors. So they're resisting, they're not using up current, but they're resisting the flow of current, right? So the total resistance of a series circuit can be calculated by adding the individual resistors, right? So if you add up each of the resistors, you will get the R total. And I'll do a quick math proof to kind of show you that you can in fact do this. I'll do that once I'm done here. But so the next question asks, as you add resistance to the series circuit, the total resistance of the circuit will increase, right? One way you can kind of like model a circuit is by like equivalent resistor. So what resistor can you put in place of these three so that the circuit behaves the exact same, right? Same current, same voltage, all that. And that is called your equivalent resistor, and that increases, right? Like your total resistance increases when you keep adding resistors. The total voltage across all the resistors can be calculated by adding those voltages of each individual resistor. So, right, 2.554, the voltage used up by R1, and then 6.37, the voltage used up by R2. If you add those up, you get the total voltage, 9 volts. The same goes here. So, adding the voltage across the individual resistors. Right now, I forgot to do 9 and 12, but you can see my equations, if I just show you my paper, it was literally just adding, like, each individual resistor. So the one right here, and then the one for 12. Alright, explain why cheap holiday lights all turn off if one bulb burns out. So really, if you know, when you plug in your lights and you have them all around, the light, your outlet is kind of like the it's kind of like the voltage, right? It's like the battery supplying the potential difference. Each of your bulbs is a resistor. So if one of those resistors, right, burns out, there's going to be no more current flowing through it. It's impossible for current to flow through it. And then, if there's no more current flowing through this thing, there's no more current flowing through here, right? You can't have current flowing here and then, you know, stop, and like kind of jump over and then current keep flowing here. No, there's no more. If one of the bulbs burns out, the whole circuit stops because the current is the same for each resistor. This guy's current is 0, so is R1 and R3, right? So that's one way you can think about it. One way I like to think about it is like if your current is like charges like marching through this whole thing. If they see one resistor they can't go through, they're going to tell everyone, hey, stop, you can't do this. And then all of them stop, right? Kind of like a leader kind of leading them. That's one way you can think about it. Real quickly, I'm just going to show you a proof if you need a. You know, you can't really, I don't like the word prove in science, because in my opinion you can't really prove anything. You can only show a lot of evidence and be super certain about something because of the evidence, but whatever. The math proof for the resistance total equation, if you think about so we know that the total voltage, so V total is going to equal V1 plus V2 plus V3 and so on, right? So, what is V1? Well, V1 is equal to I times R1, right? This is Ohm's law. So V total equals I R1 plus I R2 plus I R3 and so on, right? But what you can do is you can, you see that the current for each of these is the same, right? We have evidence to prove that, and we talked about why that would make sense, why the current would be the same. I can just factor out an I term from each of these. So R1 plus R2 plus R3 and so on for as many resistors as I have. If I divide both sides by I, V total over I is the total resistance, right? Like if you take your total voltage divided by total voltage divided by the total current, or the current, you get your R total, which is 90 or 36, whatever. So V total over I is our resistor, like our equivalent resistor, it's our total resistor, and that total resistance just equals the sum of R1 plus R2 plus R3. So, hopefully this video made sense. Hopefully I cleared up kind of how series circuits work.